Good morning, all of you. I'm Jayathilaka and I'm going to present our paper under the topic of numerical analysis of seepage condition in ancient Kalawewa Dam. The co-author of the paper is Dr. S.P.M. Sri Lankans have more than 2000 years of written history of dam construction, and they play major roles in constructing and operating large dams in the world. According to the written history, oldest dam in Sri Lanka is reported as Kalawewa, and the oldest functional dam is considered as Continuous Barrage in Syria. Furthermore, Sri Lankans have separate culture with dams and reservoir operations. Out of all types of dam, embankment dams are more common, using ordinary construction method, utilizing cheap raw materials and subsurface material for embankment construction may be the reason behind that. Embankment dams are classified into two main types called earth-fill and rock-fill dams. Seepage play more important role in embankment dams. According to the USBR, nearly 50% of embankment dam failures occur due to seepage-induced causes. Sri Lanka also have experience with dam failures. Kantale Dam was failed in 1986. Although it is not a seepage-induced failure, but a lot of consequences occur due to that failure. Many countries around the world also experience dam failures. Fatalities, property damages, infrastructure damages are occur due to those failures. When we consider about the Kalawewa Dam, it is consisting of two conjugate bodies of water called Kalawewa and Balawewa, and now it is past more than 2000 years after construction. Reservoir capacity is 104 mcm and length of the dam is about 6.5 km and the maximum bund height is about 14 meters. The dam is situated in northwest side of the Double Tout and the downstream of the Dambulla and Kandalamu reservoirs. The dam went through several rehabilitation works in 1885, 1959, 1975 and 2012 under several projects. Seepage analysis is highly challenged in Kalawewa Dam due to absence of relevant cross-sectional data, construction methodology, quality control and engineering properties of the material, and also due to archaeological restriction. Further, limited allocations are provided for operation maintenance, also a barrier. Hence, analysis of such kind of ancient dams in predicting seepage condition is not an easy task. This investigation was carried out with the following objectives. Compare of seepage observation with the results of numerical analysis under steady-state seepage condition using CW software. Investigating the effect of permeability coefficient and non-homogeneities on seepage through the dam by numerical analysis. Establish an hydraulic conductivity value that would correspond with the piezometric data and the seepage rate. Here I will explain in brief the methodology followed for my research work. Beginning, I collect available dam details. Then, for the data collection, I use literature, instrumentation data, and I have done some additional tests in laboratory also. Out of 3 sections, I select 2+713 for my research work. Then the modeling in CW was done. Then some analysis were done, and the model calibration were done. Finally, did some additional analysis, and that will be discussed in next slides. The K values found from the literature and the laboratory test values, there are huge difference. So applicability of those K values also investigate in this study. This is the instrumentation data taken from the research work for the section of 2+713 chainage. Here there are 3 piezometers installed in this section. Since there were no miniatures available to measure the seepage in this section, manual flow measurement were carried out. The time was measured to fill up 5 liters of water in the tow drain and converted to cubic meters per day per meter length. These are the input given for the CW. Sample function was used to estimate hydraulic conductivity function and sample function was used to estimate the volumetric water content function, and the Venn-Newton method was used to estimate hydraulic conductivity function. With the help of that, material model was defined. Here I use saturated unsaturated model and the KY into KH ratio as 1. For upstream, the water head, and for the downstream potential seepage phase used as the boundary condition. Further, here I insert 3 key point to denote the piezometers in the field for the model validation purpose. In the initial analysis, evaluate the applicability of permeability coefficient given by the POIRI. Kx was assigned as here 1 centimeters per second, and the reservoir at full supply level was analyzed. By this analysis, high value of flux into the tow drain gate as a result, and that is about 785 cubic meters per day. Hence, some laboratory fouling head permeability tests were done for the sample collected from the Kalawewa Dam. Since the absence of cross-sectional information, geometry model of the dam was drawn using the surveying data, and also level of the residual soil was not identified in the literature. Hence, trial and error procedure had to follow to get some reasonable bottom level for the geometry model. For future analysis, I use 90 meters as the bottom level of the geometry using the results, which is a reasonable mid-level from the result. Here, the influence of the Kx for the distribution of total head and flux was investigated. Kx was changed in the hydraulic conductive function, while other parameters and boundary conditions were kept constant. As literature says, total head values in the results was not changed with respect to Kx, but changing of Kx directly affected the Peradeniya flux. From the CW results here, it can be deduced that the K should be around 1.8 into 10 to the power minus 3 centimeters per second, corresponding to the field observation, which, however, over-predicted the total head values by about 1 meter. Here, I have done steady state seepage analysis considering the homogeneous behavior to cover all water level from 129 to 122 by 1 meter. The K was varied from here 0.1 centimeters per second to 1.8 into 10 to the power minus 3. Only Peradeniya flux was changed with respect to the K values as previous cases also. Here, the variation of observed and CW results with reservoir water level is shown. Resulted head values of CW and observed head values gives similar variation with reservoir water level. But CW results give it about 1 meter higher value than the average observed field values. And only piezometer 2.T is in the both CW results and the field observation shows a better relationship throughout the period of the observation from 2015 to 2019 with the reservoir water level. Here the variation of Peradeniya flux observed from field and the CW results with respect to the both reservoir water level and the K are shown. The Peradeniya flow rate directly relates the reservoir water level. The observed flux and the CW results are comparable when the K is between 18 to 10 to the power minus 4 and between into 1.5 into 10 to the power minus 3 centimeters per second. Now the doubt is coming whether the dam is behaving as a homogeneous or not. Observed flux at the Peradeniya about 1.4 cubic meters per day per meter length for full supply level. But when I use Foyer's K value, it is come around 785 cubic meters per day. And when I use K values given by the laboratory data, it shows around a value 0.0017 cubic meters per day. So what is the reason behind that? Although I assume the dam is homogeneous due to many reasons such as root system of the large trees, uneven surface, many other local variation, and due to aging effects, properties of the dam material may be changed place to place. Finding those variation also may not be economical by detailed science investigation, but as benefits may not be justified with the investment. With the ideas and result obtained from the previous analysis, here I have done steady state seepage analysis for the dam with the presence of hypothetical low permeable central core. Here K was varied in the core and outer section as mentioned here. From this analysis, it was possible to identify several combinations of K values for the core and outer regions which provide far better agreements with the observed and field flux values. Those coefficients are in the table as given here. One of such combination identified as 5 into 10 to the power minus 3 for the core and the 2.35 into 10 to the power minus 4 for the outer regions. And here the variation of total heads and flux values obtained for the field and CW results with reservoir water level is shown for the previous combination. So not like in homogeneous case, now the values are coincide with the actual field condition. That means the combination of K values is denote the average actual field condition of the dam. Further, unlike in recently constructed dam, an ancient dam exhibit non-homogeneities due to the changes that have been taken place over many centuries, such as particle migration, different material layer might be mixed each other, particle sedimentation, etc. However, in this case, it is the introduction of a typical low permeable core appear to be a method to reduce the margin of the variation of total head and the seepage rate. Hence, this can serve as a calibration tool for the seepage analysis of ancient dams. Following conclusion can be made from the study. Considering the homogeneous hydraulic properties, K value given by the Poirot overpredicted the seepage rate excessively, but the laboratory K value underpredicted the seepage rate. K values of 1.8 into 10 to the power minus 3 centimeters per second predicts the seepage flow rate accurately, but which, however, overpredicted the total head values by about 1 meter. Using the concept of having hypothetical low permeable core, predict the seepage total head and the seepage rate well. So this can serve as a calibration tool for seepage analysis of ancient dams. These are some recommendation may help to advance the knowledge on study area, and I will not going to discuss one by one. And these are the literature I have used. So thank you very much you to spend your time and listen for me. Thank you very much.